Yeah, we're here to talk about the SolarWinds, and probably the first question that you may be asking. Well, that happened in 2020. Today's 2025. Well, we're not here to rehash the old news. We're not here to say and revisit and do like a traditional postmortem. We're here to say and present the question of what would have happened if we could actually catch this. SUNBURST was the masterclass in evasion and supply chain compromise. And when it comes down to this, we need to ask ourselves, do we need to change anything in our DevSecOps playbook? And here I want to present the theoretical idea of, yeah, we can actually do it, and we can switch from our traditional, what's considered best practice shift left to argument left DevSecOps. But first, let's ask ourselves, well, why does it matter? Well, SUNBURST was a masterclass in evasion, compromise. It was a human operation manual. Took quite some time to complete from the very start of the kill chain to the very end of the kill chain. But it presented us with quite a lot of new findings, such as trust became a new vulnerability, and that's important. And now we can see how we can go from a traditional mindset of, yeah, maybe we need to think about zero trust to like zero trust is not optional, it's mandatory. The dev pipeline and dev environment became our new battlefield. And now we can start leveraging what our adversaries use, AI, from the blue team perspective. We can see where traditional host EDR limitations are there and how we can improve this with AI, and we can perform a lot better anomaly detections behavioral-wise and network-wise. But let's not forget about the fact that, again, SolarWinds happened in 2020. Today's 2025. While supply chain attacks are happening, keep happening, and we had just one recently, NX, early September. And the reason why I singled out this one is because it provides a very nice distinction between the SUNBURST and NX. So just few recaps to drive the point home. Number one, trust became the new vulnerability, and you can see the difference between the SUNBURST and NX, but the common theme is trust is the vulnerability, and trust is being abused. Two is we can see how adversarial tactics have changed. Now we're going, instead of stealth, we're going for a lot of automation. We don't care about whether we're going to be caught. We care about how much damage we can do in the shortest amount of time possible. And then dev pipeline became our new frontier. And what I mean by this is we can abuse our dev pipeline a lot faster. Now speaking from adversarial perspective, we can abuse our dev environment a lot faster, and that becomes a very juicy ground if I speak with my red team hat in mind. And lastly, attacks became much faster. SUNBURST was a human operation. It was very manual. And we're going to talk about the timeline really quickly on the next slide, but it took some time. NX, on the other hand, didn't. And if you go and Google NX postmortems, incident reviews, what has happened in the past and how people were able to fix it, you can see the write-ups are there. There's plenty of the write-ups, plenty of defense in-depth protocols for what you can do now. And it happened just early September, so a couple weeks ago. So like I said, let's go briefly to the timeline of the SUNBURST. Now, we're here not going to talk about the specifics of what exactly happened in each step, why it happened, and the technical beats. But we have the Q&A in the end, and I'm happy to discuss it more in depth or after the presentation. But here, what I want you to do is to take a look into this timeline with your DevSecOps hat in mind, and just take a look into what matters if you take a look into SDLC. So first thing first, September 2019. We have our group largely attributed to be APT29, or fancy bears, cozy bears, whatever you want to call it. They gained access to the internal network of the SolarWinds. And what they did, they implanted the Sunspot, which was a surveillance tool. Essentially, it monitored Orion software and processes that were contributed to be either ORIN-like or non-ORIN-like. Then they injected a couple benign strings to see if it would actually get built, executed, signed, and released. In October, the dry run test was successful, so they said, okay, cool, now we have the control of our build pipeline. Now the fun begins. A couple months later, we have the actual malicious code being inserted into the legitimate DLL file that was done for the counter-forensic step to make sure that we can evade detection, we can evade QA. Later on, we started doing the distribution. So since everything was built, signed, released, and distributed, because the build trusted the pipeline, the APT29 were able to essentially release a bunch of different versions of SolarWinds software with a backdoor in it, and the versions you can see on the slide. Later on, there was a counter-forensic step, which was literally just remove the backdoor later in June. Afterwards, we see a bunch of different clients start having this backdoor in their software. A bunch of them were infected. And essentially what happened, a short summary was you have a dormant payload. It doesn't work for the first 12 to 14 days. Once it works, it decides whether or not I should start or not start. If there are some criteria that are met, it decides to auto-destroy itself. If some criteria are passed, it decides to execute itself and essentially starts doing different processes. A couple processes that were user process behavior, that was anomaly. It was a differentiation from traditional ORIN software. It would try to set up a C2 connection, so command control server. It would perform data exfiltration steps, and just traditional malware activities. Later in December, we have FireEye that publicly disclosed the SolarWinds attack, and about a week later, we have Microsoft, along with a FireEye coordinated effort to seize the main C2 domain. So essentially, looking into this timeline, what we can say is the biggest problems. If I'm an adversary, I shouldn't be able to inject the code. It shouldn't be built, signed, executed, and released. And at the very least, I shouldn't be able to establish the egress traffic to steal the data. And all of this happens, so here's a question. Did we have any missed opportunities, and could we actually do anything about it? And basically, the answer is yes. And to sum up the slide, what we have is we have missed opportunities around the scanning, so static, dynamic, and runtime scanning, because we lacked control flow analysis and we lacked detection of anti-forensic steps such as dormant payload, removing the sunspot. These kind of missed the mark. We also have lack of anomaly detection, both behavioral and the network. And lastly, just to kind of build it up all together, we have had a complete lack of continuous security posture management. There was not a specific framework that we wanted to abide by. So the tragedy, though, was that we had all those signals in the pipeline, but we didn't have automation nor AI to react on time and to proactively defend ourselves in time. But now here's the question. Can we just say, okay, so we know all of the areas that we have missed. Can we just say to our Cursor, OpenAI, whatever, can you fix each one of those steps and just tell us what's the perfect DevSecOps playbook is? Is there a better version of SDLC that we can think of? Well, no, we really cannot do this. And the biggest problem is AI tends to hallucinate, and hallucinates a lot. Yes, we can bypass it by using RAG models and things like this, where we train it on a very limited amount of data, so we can kind of minimize hallucinations. However, what we can do is we can redesign DevSecOps playbook where AI is our first-class citizen. So now we're treating it from the runtime to the release all the way. And then the AI just no longer scans code, but it verifies provenance, looks for any drifts, and detects anomalies. So let's see how we can actually do this. So here's a proposed scenario for AI-augmented DevSecOps. So we have a traditional step of looking for the source control, build, and release. This is what you usually see in our traditional SDLC. In other words, we have design, develop, deploy, and maintain. But now we're saying, hey, how about artifact registry and rollout, adding as another step. And now we want to add runtime and post-installation customer defense in depth. So what we're saying now is we're increasing the area of DevSecOps ownership in this case. Now, this is not comprehensive because we also need to remember how threat intelligence and detection engineering can help us if we have a closed loop. So what I mean by this is we have the beginnings of a new way of AI-augmented DevSecOps, or another way, AI-augmented ThreatOps, which is DevSecOps 0.2, where we see our traditional look into the code, build, release, post-installation defenses for customers, artifact registry, as well as threat intelligence and detection engineering that proactively identifies threats and feeds it back to our source control. And this way, we can proactively react to APT groups, we can proactively feed and create IOCs. So let's actually take a look how we can make this work each step at a time. So before I go and dive any further for this slide, because we're going to have quite a few of those slides with suggestions, I just want to kind of present the structure of how I structured all of the suggestions. So in the beginning, where the light bulb is, this is the goal of a current stage. Then when you see the notepad, this is different signals that we can collect. At the bottom, you see the suggested model that we can use. On the right, you see this little action or gate. This is the action or gate that we can implement in mind to think about how we can actually implement this. And in the end, the question mark is, well, why do we care? Why should we do this? So number one is goal-built anomaly detection. Arguably, probably the most important and the first step that anyone should do in their organization is just to see what is normal and what is abnormal in your build. The problem was the sunspot implant was actually successful because build implicitly trusted the pipeline. And if we look into it from the perspective of the opposite, where we assume breach, we assume danger, we assume the threat, we can never trust it, but what we can reference is our golden build, the only thing that we can trust. And we can collect different signals. We can use our, in this case, suggested unsupervised anomaly detection to see if we find enough deviation from our golden build. Essentially, we just quarantine the artifact. We page ping release manager and figure out what to do next. Next step is looking into guardrails on provenance and attestation. Those two frameworks are just a suggestion. There are many others that one can use, but those ones are fairly big and well-known. And this step is actually very different from any other step just because we're using the RAG model here to train our models explicitly on either SLS or SSDF to ensure that it doesn't hallucinate. And basically, the idea is the build should never be trusted, and therefore, each time that we have any sort of tampering attempts with the builds, we can easily identify it by looking into our provenance. And if it's not verified, we essentially block the build. This one is binary to source consistency checks. This one is still a research prototype, so this one is the one that's probably the hardest one to implement in the organization at the moment. The reason for it, again, even though it's in production in a lot of companies, it's still actively being developed. And essentially the idea there is simple. Because with the SUNBURST attack, the inserted code was not a part of the reviewed code, what we can do is we can say to ML, hey, can you actually align our AST to our CFG? So essentially compare our source to the binary and see if there's any alignment or misalignment. This way we can prevent any sort of ephemeral code injections. Here we have a very basic representation for what happens if you are creating the payload, especially if we're talking about advanced hacking groups. They usually have some sort of obfuscation techniques. They have time-delayed mechanisms. So here we're essentially just looking for any sleep patterns, any sort of timers, any of those things, and regular ML classifiers can work on this. This is a very straightforward problem to solve, and we already have solutions for this. This is a hot take for this pull request review. So essentially, since AI can produce a lot of false positives and also can create false negatives, tends to hallucinate and a lot of other things, this is arguably one of the hot takes where we're saying, hey, AI can actually do your PR reviews, but not in the way that you think. If we look into explicitly high confidence suspicious code pieces and we train our models on what we think is explicitly bad, then we can say, hey, at our first stage, AI will take a look and say, here's some high confidence findings that I think are not good, and I would like our AppSec to actually review this. So we have the second stage where we have human in the loop. And this way we can eliminate quite a bit of the noise, just because a lot of ways we can sift through the false positives and false negatives fairly easy here. And the last piece for the source control built-in release stage is dependency and third-party risk with GraphML. So if you visit the hall, you've seen so many companies already trying to do this and doing it successfully, which is literally just looking into our third-party libraries and seeing, hey, is this an odd package? And what I mean by odd package is the maintainer still working on this? Is the maintainer been compromised? Okay, if everything is fine, do we actually see maybe some typo squatting, maybe some dependency confusion issue, or any sorts of that? And while, yes, we can use some of the vendors explicitly and say, hey, this can actually work, no problems, the problem becomes in some companies where it's a very tight dev environment where you cannot simply just integrate another tool. You really need to think about how can we make this work in a way that's not going to jeopardize developer velocity, but at the same time will achieve same or similar results. And this is where we can just look into our GNNs and just do the work. Looking into our next stage, so artifact registry and rollout, we can just perform regular attestation-aware progressive delivery. So what it means is that we have just looked into our previous stage with 6 different methods and 6 different ML models that can perform and give us some sort of risk. And now here we're saying, hey, can we actually infuse it all together and have a single readiness metric? So yes, we're talking here about risk fusion engine, where we feed everything from the previous stages to say, is this okay to roll out? And if it is, we can just do regular progressive delivery. And what I mean by progressive delivery is canary to telemetry tenant first, and then if no deviations are found, we proceed with a traditional rollout. If it fails, then we can just auto-revert it. Looking into AI-assisted binary diffing, this one is a very interesting way to take a look into how different builds may subtly change over time and how this can help, especially looking back proactively. So let's say we're going back into our timeline of the SUNBURST, and we're talking about almost December, November, December of 2020. And we can take a look with this binary diffing between the releases, and we can say, hey, actually, there were some problems all the way back in June by this. And this becomes a very tedious task to do without enough signals. And with this case, with enough signals and having LLM being ST aware, the problem becomes very solvable. Here we can look into DNS and DDA anomaly detection. And essentially, in simple terms, this is just network anomaly detection. We're looking into our DNS logs. We're looking into our DTA classifiers. We can say, hey, let's use unsupervised model for our DNS logs and to say, is there anything that's sketchy? Looking and having a little bit of supervised learning for our GTA classifiers, and we're set. Looking into how EDR traditionally has quite a few limitations, here we can actually see, could we take a look into every single process within the system and treat it like a separate identity? And if a separate identity performs any other way than the one that's expected, we can flag it, we can out-isolate it, we can capture memory for forensics, do whatever things we want to do. The most important part is we can actually be a lot more proactive and figure out any behavioral anomaly detection right on time, right in place, and block egress immediately. And looking back into kill chain events, if everything else is successful, but you block the egress, the whole operation is pretty much at stake because you really cannot steal if you have blocked egress. Lastly, we can take a look into the lateral movements. In a kill chain of events, you usually want to perform some privilege escalations, and that's what every single APT group does. But essentially, what if we ask ourselves, how about we try to be more proactive and try to figure out our trust edges and see, are there any impossible trust paths that we can actually achieve? And if there are, we can pretty much just block those trust edges right on time and out-enforce just-in-time provisioning, making sure that essentially we have less privileged, but a lot more proactively. And here we come at the threat intelligence and detection engineering. And if you've ever worked in Dart, if you ever worked in threat intelligence, you know how much time it takes to write very high-quality indicators of compromise rules and things like this. You may also be aware that IOC depreciation is a big problem. When you look into new vector, when you look into the new threat, you have to create a new rule. You have to write it in a high-quality manner. And then the next day you wake up and you have to write 10 more rules, 10 more indicators of compromise, and try to fit it into your Dart systems. And the problem here is, yeah, sure, we can do this, but can we actually do it effectively? So the suggestion here is we can leverage AI for looking into a whole RSS of different threats that we can take a look proactively, read, and see if any of them align to our organization, auto-write the IOC rule to make sure it fits into whatever system you use, and then you can update your hunting playbooks, you can take a look into how it may change your development strategy. But the fact of the matter is, you can start doing proactive hunting in the matter of hours instead of the matter of weeks. And lastly, you can perform the posture gap analysis, making sure you're verifying your provenance all throughout the cycle and not just the traditional part of SDLC. So to sum up, just because there was quite a bit of information, we have few areas where SUNBURST succeeded. So the very first one was building the hijack, or with the Sunspot, the dry run test, the dormant payloads, and things like this. Then there were some updates that were signed because the build pipeline explicitly trusted. Then we have our stealthy C2 using DGA, and essentially the egress was not blocked, and the C2 was successful. And lastly, there was a framework misalignment. And we've just taken a look how all of those things can map together through several suggestions and several suggestions using the ML, where we can make it work in some ways a little bit better, in some ways a lot better. But the point of the matter is, when we put more defenses and more layers, there's not a single point of failure. And that's the key where we want to leverage AI. We want to make sure that there's not a single point of failure. However, the problem becomes, hey, we have our traditional SDLC, which is fairly easily achievable. We have our DevSecOps department. Maybe we have our AppSec and InfraSec working together. It's fine. The perimeter is not that big. But with this new proposed DevSecOps playbook, it becomes huge. Now we have to engage our Dart team, maybe SOC team, maybe threat intelligence team. We definitely need to engage our offensive security team. And that becomes problematic. But security is not a one-team problem. Usually you want to take a look into the whole plan for the entire organization and treat security as an enabler. And how do we do this? We can do this by simply figuring out who is responsible for a certain area, and responsible is the one who executes day-to-day tasks. Who is accountable? The one who ultimately owns success or a failure. Who is consulted? The one who gives some expertise and some advice, and the one who is informed. The one who should just be aware of what's happening. So yeah, I'm talking about the RACI doc. So here we have just a simple RACI doc with some control areas. And if you take a look into the control areas, they sound and look a lot more traditional DevSecOps, which means we have our traditional source control, we have our traditional build pipeline, artifact release, testing and QA that happens all the time. We have our deployment and operations, runtime, and governance. So what I did here was to digest all the areas with the new DevSecOps playbook in mind into a little bit more digestible areas here, looking into and providing a specific measure for each control area that you can use, and suggestions for who should be performing day-to-day tasks, who should be owning the risk of failure, and who should be consulted and informed. Now, all of this is good, but if we sum up and recap, so we talked about the SUNBURST, we talked about the timeline of events, what happened, we talked about the problems and missed opportunities, we talked about suggestions on how we can make really good changes in each one of the areas, and we have RACI doc. What we're missing is how can we actually put it all together, the POC. And the problem with POC is we actually have quite a few ML models. So here's the idea of POC, and that's very doable. It's actually running in quite a few areas already in production. And the idea there is actually fairly simple. It doesn't change much from what we traditionally do with our ML engineering. The only difference is we have hermetic builds for the ML models. We have zero trust between the planes of each of ML model. The key areas and the key principles here is we ingest a bunch of different logs into our secure data lake, and we use our save, signed, append-only store. So nobody can steal the information in that store. Then we have our model train, and we have different models that we can use for different behaviors that we have mentioned before. Some are used for third-party library prevention, abuse. Some are used for trying to figure out any trust edges and impossible trust paths. Some look into control flow analysis. And some are just simply aligning AST with the CFG. Later on, we'll look into our model registry. And that model registry essentially stores signatures and attestations for our models. Think about it as software supply chain for your models, so to speak. Then we have our serving and policy, and essentially there what we have is we have our risk fusion engine that we talked about earlier that combines all the results of every single ML model to figure out if we can promote the deployment, if we can block the deployment, or if we need to do anything between ready for deployment before actual deployment. And with this idea in mind, CI/CD doesn't just scan and perform simple what if else statements. It decides and gives you quite a bit of justification per each of the stage. And the thing about it is that even if 1, 2, or 3 models fail in providing you with the output and creating false positives or hallucinating, because you have the risk fusion engine, because you have RAG-based verification for your provenance, you still combating a high amount of false positives here. You're combating a high amount of noise by making sure it's all tightly knit. You are expecting that threats are going to be happening in your environment, and you are trying to proactively hunt them. So to sum up, here's some sound bites. Sign doesn't mean safe. Attackers can weaponize trust itself. We have seen it with SUNBURST. We have seen it with an X attack. We have seen it with so many other supply chain compromise. CI/CD pipeline becomes our attack surface, so we should treat it like a battlefield. And lastly, if you don't hunt your threats, your adversaries will. So here's the suggestion of the DevSecOps version 2, where we look into AI augmented threat ops. And the reason for calling it threat ops is because we are proactively assuming breach, proactively identifying threats, and trying to hunt for those threats just on time. All right, thank you for your time. And
Did it work? Thank you. So first of all, thank you. Great presentation. And so I saw a lot of different types of models there, right? That makes a lot of sense. But let's say we have an organization that doesn't have ML team and a lot of expertise. Would it be fair to say that it's doable to deliver something similar using, general LLMs? Maybe smaller ones, cheaper ones, I don't know, GPT-4, or, they have nano models and whatnot. What do you think?
Love that question. Thank you. So it's possible. It will have its limitations, of course, and it's important to figure out the number one risk you will be facing is hallucination, AI hallucination. And you may be risking of becoming, instead of security enabler, you're becoming security stop, security gate, and that's going to be pretty dangerous. However, one thing that you can do with essentially any AI model with regular Gen AI is, number one is just golden build anomaly detection. That's first and foremost, and that one is a pretty straightforward thing to do, because just training it on your AST-aware syntax, making sure that your code base is trained fairly thoroughly, and at the same time looking into what kind of deviations you can see, it's fairly easy to achieve. Some of the other ones are not as easy to achieve. So the one that I definitely do not recommend is AI and PR reviews. So if you do that with a regular Gen AI, I don't think it's going to work at all. And lastly, looking into diffings and differences between the diffings, so between each of the releases, where essentially we compare the AST to CFG. That becomes very troublesome because, first of all, it's still, research is still being done. So it's very hard to configure it correctly. And to the regular traditional like GPT-4s, I have very little faith in them making it work well.
Yeah. I thought that was great. Are you going to share your slides?
Slides? Oh, yeah. They'll be shared after I think the whole SecTor is done. Okay. Offline, I think about a week or two.
How would we get them?
Oh, just on the SecTor website, I believe.
Cool, thanks.
Thanks for the presentation. I was wondering, while we are securing our CI/CD pipelines like this, should we assume breach in the sense that the attacker has already infiltrated the internal network of ours, right?
Mm-hmm. Yeah, good question. I actually love this question a lot because it's a hot take, right? Everyone will have different takes. My take is, yes, we should always assume that stuff already happened. And with this in mind, that should bring us some sense of urgency, not in a way where we're panicking or anything like this, but a sense of urgency of, hey, maybe insider trust issue. Maybe we have internal employee who is disgruntled and wants to do some damage, because that does happen fairly often. But it can also give us a sense of urgency to take a look into truly zero trust, where we trust essentially nobody because the breach has already happened. And that's the true definition of assumed breach. And I think that's helpful just because it helps us to take a look into it holistically and do a truly defense in depth.
Got it. How do we explain the developers that the CI/CD pipelines that they're dealing with are not automatically safe because they are internal? You know, most people assume we should just, you know, secure the platform itself. But as long as it's secure, it's all safe. That's this illusion of safety.
Yep.
So how do we overcome this illusion to essentially deliver this sense of urgency to the developers that we need to secure the pipeline itself, not just, you know,
Yep.
the development platform at large?
Yeah, great question. So I have two suggestions. One is anecdotal, so just a story of mine, how I was able to achieve it, and the second one is more generic one. I'll start with the generic one because I think that applies generally to just in general. So taking a look into performing threat modeling and just saying, here's insider threat abuse, here's outsider threat abuse, specifically targeting CI/CD, specifically targeting dev pipeline and dev environment, and showing it from the threat perspective. That seems to be fairly effective. The other example of what I've done in the past that seemed to work the best for developers was to actually hack stuff. So with one of the organizations that I worked in the past, they didn't have a very good hygiene around GitHub runners. So what I did was creating a new account on the GitHub. They didn't have access to the organization. They did have some access to open source projects on the GitHub, and just I took over one of the GitHub runners, was able to show the impact, was able to read some of the secrets, abuse secrets further, compiled this into one report, showed it to the developers and said, hey, we have a problem. I shouldn't be able to take a look into your AWS account without problems, you know? So just taking a look into this and showing the actual abuse and looking at it from perspective of, can I abuse the GitHub runner, and taking it one step further to saying how much damage I can actually do. So going from a traditional red team operation to more of exploit development to showcase the true, real, biggest impact will speak to the developers the most, I believe.
Thank you.
Hi, thanks for the presentation. My question is, what was the overhead of all these added processes to the build pipeline, and how was the reception from the engineering teams with this extra process?
Yeah, great question. So there's quite a bit of overhead, specifically looking into the diffing. So looking how different build releases are sadly changing, because that's a very CPU heavy intensive work. This one is the only thing that's like, I guess, lesson learned that I recommend not to do it for each single release, but looking into it in a more conservative way. But everything else did not require too much CPU power as long as you are having fairly good structure of each of your models and making sure that they are on separate planes, that there's zero trust, and it's a traditional hermetic build. It shouldn't be too much of overhead. Now, from perspective of developers, I think mostly everything was perceived fairly good. The hardest part was making sure that we showcase the value in verifying provenance. But again, this one can be demonstrated fairly easy to say, hey, can I actually abuse some of your stuff in a way that you don't see, such as, can I change and inject the code where it wasn't reviewed in the first place? If I'm able to do this, then the developers will be like, oh yeah, we're actually missing verification of provenance, and let's do it. So for the most part, it's fairly straightforward. However, I do have to say one point. From perspective of security, I do think that there's new, so to speak, discipline of ML security engineer, where it's kind of expected of you to know your ML models well and make sure that you can spin it up in the same level or better than a traditional ML engineer, to ensure that you can speak the same language to ML engineers. And essentially taking a look into this the POC, being able to reason with each of ML engineers and to say why it's necessary, why each model is exactly that. Why do we need Siamese model versus transformers and things like this?
Thank you. Do you have any metrics that you could share to help support like implementing those processes?
What do you mean?
Like the benefits of not having this implemented into the pipeline to having this implemented?
I don't have any metrics currently, but the idea there simply is that I don't really think that there might be necessarily any metrics, because it's really hard to measure what is something that you don't know what to catch. Because if you don't have the controls in place that are AI augmented, you don't really know what you don't know. You don't really know what you cannot catch, right? So gathering metrics in general is a bit more cumbersome. However, I think looking into the developer velocity metrics would probably be a really good metric here to add, aside from security, because we want to ensure that we're not being a blocker. So yeah, this is something to think about further. Yeah, thank you for bringing this up. Thank you.
I'm interested in the conservative version of the code diff you were talking about. Our company does a lot of the code diff analysis, and you said you don't recommend it, and there's like a more conservative way to do it. Can you expand on that?
Right. So good question. Thank you. So essentially, each time that you take a look into each diff that's being implemented and use all of the CPU power, so using all of those steps together for each of the checks, it's going to be pretty CPU costly.
Yeah.
However, taking a look into maybe everyone is going to be doing diffs to the staging environment, and then you have a staging release that's going to go back to the master. Doing the checks over there against the master would probably be a better choice, just because it's more CPU conservative, but also you can easily auto-revert for each of the branches that do make a specific difference. And since we are using quite a few supervised models, we can easily backtrack the data based on the data labeling.
Okay, I see. Yeah, thank you.
Yeah, thank you.
I have a sort of two-part question. You obviously went down the AI path. Did you consider not using AI or ML as part of more like traditional statistics like Bayesian or something like that to be able to identify maybe anomalies that were possibly injected?
So you're asking?
Non-AI based methods.
Yeah, of course. That's what is being used currently, and this is just an approach of how we can AI augment to figure out how we can catch more anomalies.
And when it comes to bringing this on with a team that doesn't have the existing AI experience, doesn't have an ML team coming in from zero, sort of timelines or expertise that the organization would need to have to be able to adopt this? Is it like 5 years and a couple PhDs, or is it like a couple intermediate developers in 6 months?
I see. I think it's really hard to calculate because depending on the organization size and needs, there might be different effort. When we're speaking strictly at the organization that's not, I guess, AI receptive or AI adopted, I would say looking into each of those control areas and taking a look at the one that's probably the most important would be like source control, and starting there would probably be good, because in either case, iterative steps towards doing better is better than doing nothing. And where we can see some limitations of AI and some dangers of AI, because you're right, there are some benefits of not using AI because of the risks of AI hallucination and other things. However, if we don't embrace it early on, I think it becomes a very difficult ticking bomb that we'll have to address later on. So just picking one of the control areas and doing it one by one would probably be beneficial. And in terms of the effort, I don't think it really takes that much. I mean, it can be started from a regular security engineering department that is heavily invested into AI knowledge and starts to learn more and starts to experiment with this more, and little by little you can start adopting more and more into your SDLC and see how that works. But you don't necessarily need PhDs. but you do need a decent level of understandings of how AI works other than just, Gen AI prompts.
Thank you.
Thank you. I think that's it. I think that's time. Thank you.